fraction that contains another fraction in its numerator and or denominator. It can actually be both. You can have a couple of those sort of all nested in one big fraction. And we'll talk about how to simplify those a little bit more, like I said, for the whole class. We'll go ahead and do those probably Wednesday and Thursday this week. But our overall goal, eyes on the prize, what we are doing in this section is adding and subtracting rational expressions. And you might remember that by the time you go to take your Chapter 8 test, ultimately what you're going to have to do is simplify, multiply, divide, add, subtract, and solve rational expressions and equations. So those are the things that we're kind of trying to get you to do before the end of Chapter 8. Now with that being said, you might recall that when I taught you the lesson on simplifying, multiplying, and dividing rational expressions, I started with just numbers to make sure that you could divide two fractions or multiply two fractions. I'm going to do the same now. Before I get into adding and subtracting rational expressions, it's not a bad idea to talk to you about adding and subtracting fractions, you know, what you kind of know how to do already. So you don't need to write this down. This is kind of purely for your visual entertainment. Okay. So first things first, I'm going to pick real simple problem. I'm going to do, for instance, 3/8 plus 1/8. Can anybody tell me how to add those two fractions together? Go ahead, Molly. Yeah, very good. It's kind of like cake, or maybe you had some nice pie, you know, over the spring break that we just had, quote unquote. If you had 3 out of 8 pieces of pie, it's both delicious and very satisfying. And then, oh, you liked another slice of cake or pie, whatever you had. If you had 3 out of 8 pieces and then you took another 1 out of the 8 pieces, you had a total of 4 out of the 8 pieces, or half the pie or cake, if you recall. So notice we don't do anything with the denominator. It just kind of comes along for the ride when that denominator is the same. Okay, so that's version 1 on adding. Okay, now patience. Pick a fraction for me. Take it easy on the old girl. What is it? 3/5. Okay. And I need a fraction with a different denominator from Madison. 1/2. Okay. First question about this problem. Can you follow the same protocol and just add straight across the top and straight across the bottom? No, Claire, you shook your head. No, for sure. That is correct. Do you remember what you have to do first in order to add these fractions together? Good, Molly. You have to get a common denominator, right? In other words, an LCM or an LCD, just like you found on your assignment from last night. What is the least common multiple for 5 and 2? Good, patience. It is 10. Yeah, that's the smallest number they both go into. So what we actually have to do, step 1, we found our LCM, right? Step 2, you rewrite these fractions so that they have that LCM as the LCD. So in other words, we're going to rewrite both of these fractions so that they have 10 in the bottom. So if I want to rewrite 3/5 so that it has 10 in the bottom, essentially I need to multiply the top and bottom of that fraction by a factor of 2. 5 times 2 gets me the 10 that I needed on the bottom, and then 3 times 2 gives me a 6 on top. So 3/5 and 6/10 are actually the same fraction. They're just written in a slightly different way. If I wanted to turn the 2 into 10, I'd have to multiply the top and bottom of this fraction by 5. So essentially what I end up trying to add together is 6/10 and 5/10. Now I can follow what I did in the previous problem, right? I can just go ahead and add straight across the top, 6 plus 5 is 11, and then bring the denominator along for the ride. So we actually get 11/10. And you can leave it like that. You don't need to change it into a mixed number. So again, step 1, I found an LCM. Step 2, I rewrote my fractions so that they had the common denominator in them. And then step 3, I added. Just combined my numerators and brought across my denominators. We'll do subtracting in a second. I'll hold off on that for just a moment. But yeah, let's talk about how do you add these things. Does anybody have any questions on how I did it with numbers, first of all? I followed the exact same, it's called an algorithm. I follow the exact same step-by-step process when I go to add rational expressions as well. So you're going to see that throughout the course of today, we start adding these things. When there's X's and A's and B's and C's and D's, we follow the exact same steps we do with numbers, even when there's letters in the problem. Okay, so with that, yeah, when we add or subtract, when we have like denominators, so there's kind of two cases you need to think about. There's like denominators and then not like denominators. When we add or subtract with like denominators, essentially we simply add or subtract their numerators. Then we place that result over the common denominator. Keep in mind your denominator really can't ever be 0. Can't divide by 0. We've talked about that. So for instance, if you have A over C plus B over C, that's just going to be A plus B all over C. Just combine your numerators together with an addition sign, and then you bring along that common denominator. When we subtract and the denominators are the same, very similar process, you would just do A minus B over C. I'll show you a little trick to get around any sign mistakes in a little bit with the subtraction, but it's basically the same process. Okay, so with that, we have our first example, right? In example 1, we are asked to add when the denominators are the same. When you add or subtract, to be very honest, that's where your eyeballs need to go first. You need to check those denominators. If those denominators aren't the same, well, then you have to do what you did last night. You have to find that common denominator. But for right now, they are the same. So I'm going to follow the process that I just outlined in the previous slide. I'm going to add straight across the top and then bring the denominator along for the ride. So I have 9 plus 2 over 6x. That gives me 11 over 6x. The last thing you have to do before you circle that guy up and make it your final answer is you need to check to make sure it doesn't reduce. Well, I look at this guy here and I'm like, 11 and 6? Can't reduce those at all. So that actually stays put. That is your answer. The sum of those two fractions is 11 over 6x. Questions about that? Okay, so now we have to talk about when the denominators aren't the same. And you're going to see that to add or subtract two rational expressions with unlike denominators, step 1 is going to be to find that least common denominator. We also called it on Friday's lesson, or during Friday's lesson, we called it the least common multiple. After you do step 1, after you find that LCD, they give you a second sentence there. Step 2 is to rewrite each of those fractions so that they have that LCD in the bottom. And then the third step is you actually then perform the addition. So this is kind of like this first paragraph here is step 1, second paragraph here is step 2, and then the third step is actually doing the addition or subtraction. So how this comes to look, you might see that initially the denominators were not the same. So they just multiplied the C times the D to get the least common multiple. And then you'll see that if they wanted to turn the C into CD, they had to multiply the top and bottom by D. And then this happened also with our CD here, right there. We needed to multiply the top and bottom by that C for the second fraction. And then now you can just add, now that your denominators are actually the same, both have CD in the bottom there, you can just add straight across the top. So this is going to look like AD plus BC over CD. You'll see that in the subtraction line, though, they make you work for it a little bit. You see that? So if you wanted to subtract A over C minus B over D, you got to get the common denominator, which would be C times D in this case. And then when you rewrite that bottom by multiplying that factor of D on, which due to the bottom, you had to do to the top. So the D goes to the top. And then you'll see in the second fraction, I multiplied by a factor of C, so I have to multiply by C on top. And then you just subtract AD minus BC over CD. So that's how your textbook editors take care of showing you how to add and subtract fractions, but I'm going to show you a couple of examples to help you make sense of that process a little bit. So in example 2, you'll see, holy cow, the denominators aren't the same. That's where your eyeballs need to go first. You folks know that on a test or a quiz, you know, it's not all chunked out into these nice little pieces where, oh, you know, it'll say example 2, the denominators aren't the same. That's something you have to figure out on your own. So I'm trying to teach you today that your eyeballs need to go to the denominators first. If the denominators aren't the same, you probably let out a little sigh because there's a little more work involved. You have to find that common denominator in order to be able to add the fractions together. So you'll see here they talk about step 1 in that line that they have typed out right there. Step 1 in this particular process is to find the least common denominator. So I'm actually going to go ahead and let you do that. I need you to find for me the LCD between 4x squared and 2x squared plus 4x. I'm going to pause it for a second. As I walked around, it looked pretty good. Yeah, the LCD in this case is going to be 4x squared times the quantity of x plus 2. No questions about that? We're good? Okay, so after you do step 1, find the LCD, you might recall when we did our slide a few moments ago, after you figured out what that common denominator was, you had to rewrite your fractions so that they had this common denominator. Remember, when you changed your fractions, you multiplied by the missing factor on the bottom and on the top, essentially multiplying your fractions by a factor of 1. So, you know, that's going to be the trick to rewriting our fractions here as well. So I'm going to go ahead and bring down my math problem. And this would be step 2. Here's me rewriting my fractions so that they have this common denominator in the bottom. The first thing I do to start this step 2 is I bring down the original problem. And you'll see that I make my fraction bar a little bit longer. And I always bring down the factored version of the denominator so that I know exactly what I have to multiply by, exactly what's missing. So as I compare now with my eyeballs, this 4x squared to this LCD of 4x squared times x plus 2, I have to ask you, what's missing? I need to get 4x squared to turn into 4x squared times x plus 2. What's missing? Ooh, he's not here. Sorry. Thank you, Claire. So what's missing? Compare 4x squared to 4x squared times x plus 2. Well, what's missing? X plus 2. Now it's my LCD. Remember, what you do to the bottom of a fraction, you must also do to the top. So I can't just arbitrarily put this x plus 2 here. That would mean I would be changing the original value of the original fraction, and you can't do that. Keep in mind, x plus 2 over x plus 2 is just 1, so I didn't change the value of the original fraction. I just multiplied it by 1. Now I have to change my second denominator, which is 2x times x plus 2. What do I need to multiply this guy by? This guy right here. What do I need to multiply him by in order to get him to be the LCD? How do I turn 2x times x plus 2 into 4x squared times x plus 2? What do you think, Claudia? By 2x, perfect. What you do to the bottom of a fraction, you should definitely also do to the top. And then you can put this in parentheses because you're going to end up using the distributive property. Any questions so far? Okay, now you're going to use the distributive property so that you can get some terms to add into step 3. So I am going to go ahead and expand my numerators. So I'm going to have 5x plus 10 on the top over my LCD of 4x squared times x plus 2. And then I'll distribute my 2x in. So I have 2x squared plus 2x. And that's also over now 4x squared times x plus 2. And you're like, all right, the denominators are the same. Woohoo! So now your denominators are the same. Now you can just go ahead and add. It's kind of nice. So when we add, quite literally, I just put the two numerators together. So I have 5x plus 10 plus 2x squared plus 2x. Now you wouldn't leave me an answer that looked like that now, would ya? Thinking most of you would go ahead and combine your like terms. So you want to simplify that numerator a little bit. For instance, I see a 5x and a 2x that I could put together. And then you'd also write it in standard form. So I would rewrite this as 2x squared, because that's my degree holding term. 5x and 2x makes 7x. And then you would add on your constant of 10. And then that's still over my common denominator of 4x squared times x plus 2. Notice that denominator just kind of carries along like it did when we were adding regular fractions. Then I try to factor. So thinking about factors of 20, I could add up to 7. Not really coming up with anything. I don't know about you. I don't think of any factors of 20 that could make 7. So this is actually done. I can't do that simplifying step that we did at the very beginning of this half of the chapter. So this actually is my answer. I can't simplify that. Can't cancel the 2x squared with 4x squared because, well, hey, 2x squared is a term. This is done. So again, just to review the process with you. Step 1, we had to find a common denominator. Step 2, we rewrote our fractions so that they had this common denominator. Step 3, we expanded so that we could add our fractions together by combining the numerators. And then we simplified. We tried to anyway. Didn't work out because we couldn't factor the numerator. So that's done. Questions about the process or the problem? Okay, so now we have to subtract, right? So really, subtraction is exactly the same, you might recall, until the very end. So back on my slide a little bit ago, I said, hey, I'll remind you of how to do addition and subtraction with some fractions. So we're going to talk about subtracting. And Jackie, pick a fraction for me. 3/4. We're going to subtract. And then I want different denominators. I think the same denominator. You guys have a handle on that. Brian, give me a fraction. Got a different denominator besides 4. 1/2. Okay. So here, step 1, again, I can't subtract these fractions right now because they don't have the same denominator. So the LCD between 4 and 2, you might recall, would be 4. So 3/4 is fine the way it is. However, if I want to get 2 to turn into 4, you'd have to multiply the top and bottom by a factor of 2. So you end up with 2 out of 4. The last step, how this is different than adding, is you do just subtract straight across the top. So you end up doing 3 minus 2, which is 1. And then the denominator still comes along for the ride. That's 4. So 1/4 is your answer there. Okay. So that was subtracting with fractions. It wasn't different than addition until the very end. Well, same thing with subtracting rational expressions. Step 1, you have to identify a common denominator. So right now, as I look at it, I'm like, oh man, like those denominators are different. When I go to identify my least common denominator, the first thing I do is I factor these denominators. So I'm going to look at 3x minus 9. I see a GCF of 3. So I pull the 3 out. And that first denominator factors to be 3 times the quantity of x minus 3. X squared minus 9, that's a difference of 2 perfect squares. So that factors to be x plus 3, x minus 3. When I go to find my LCD, I bring down the first denominator. Thank you very much. So when I go ahead and find the LCD, I bring down the first denominator. And then I compare it with what's on the right. So if I look here, the factor that I'm missing to get the common denominator is just this factor of x plus 3. I'll bring that down. And that's my LCD. Now I'm going to go ahead and rewrite my fractions. Step 2, I have to, rewrite my fractions so that they have this common denominator in them. So the first fraction was 7 over 3 times x minus 3. And the second fraction was x plus 4 over x plus 3x minus 3. Now I have to insert the factors that are missing to get back to my LCD. So if I look, right now I'm trying to compare this line here to my LCD, and I have to insert anything that's missing. So what's missing? Good, patience. Yeah, factor of x plus 3 is missing to make this match my LCD. Do you see how it matches now? They have to be the same. Okay, what I do to the bottom of a fraction, I also have to do to the top. So I have to insert that factor of x plus 3 on the top as well. Okay. What's missing in my second denominator there to get them to match? Got patience? Yeah, a factor of 3. And you know that we're going to eventually distribute, so you could always put that in parentheses and insert your factor of 3 on the top as well. Okay, now I'm going to distribute in order to sort of prepare to subtract. So as I look here, I have 7 times the quantity of x plus 3. That's going to make 7x plus 21 over my LCD. Bring down your minus. And then I'm going to distribute my 3 in. So that's going to give me 3x plus 12 over my LCD of 3 times x minus 3 times x plus 3. And now I can subtract. Be careful, when we subtract polynomials, you got to watch your sign. When I subtract these two fractions, here's how that's going to look. Bring down the first numerator, and we're going to subtract the entire second numerator. So I put my second numerator in a set of grouping symbols. That way I don't make any sign mistakes. And then it's a fun fact that you now need to sort of distribute that subtraction through. Now most of you could just subtract 7x minus 3x and 21 minus 12, and that's fine. But when it's bigger polynomials, this is just a really safe bet to do the problem this way. That's why I'm showing you this little trick. So you can go ahead and distribute that sign in, and then basically it's just an addition problem in disguise. You're just kind of combining your like terms. So 7x take away 3x is 4x. And then 21 take away 12 is 9. And then again, I'm trying to see if there's any factors of 4x and 9, and there's not. So that's done. So remember that you're subtracting that whole second numerator. Watch your signs. Distribute that negative all the way into both. Okay, questions about that? Because that is our last example of the day. Okay, so you have a little bit of independent practice. You'll see that you're going to start them now. We have about a minute or two left. And then we're going to finish them as our warm-up for tomorrow. And then tomorrow is very much just a practice day with this particular skill. You have bookwork tonight, so we'll go over bookwork also before I unleash you on a worksheet. Make sure that your bookwork looks good before I actually give you some more practice. You do have some bookwork tonight, and we'll talk more about that tomorrow. Okay, so as promised, I said I was going to keep recording after you folks left me today. For the sake of those that are going to be in Orlando this weekend, then some other folks are going to be out here and there for some field trips this week as well. But the first thing you're going to want to do is check over your independent practice problems a little bit. So this would be a good time to press pause and make sure that you have those answers correct. So looking those over, make sure you have those right. And then we have to talk about simplifying complex fractions. So, if we're operating under the premise that addition and subtraction went well for you, this is just very much the next logical step. And just to read it over with you, and you kind of had this vocabulary word at the beginning of the section. A complex fraction is just a fraction that contains a fraction, again, in its numerator or denominator. So to sort of build off of that definition that you copied down a little bit ago, we have sort of a step-by-step process again for how we simplify complex fractions. And a complex fraction is just simply defined as a fraction that contains a fraction in its numerator or denominator. And we actually have two methods for simplifying those. Method one is to just do the math problem that's in the numerator, and then do the math problem that might be hanging out in the denominator, and then divide your two resulting fractions, which actually in essence means multiplying by the reciprocal of the divisor. And then method number two is a bit of a shortcut. Method one is usually the more popular choice among the kiddos that I teach. But method number two, you know, it's out there and you could definitely use it. Method two is nice to show you now because it's going to help you a lot with 8-6. But essentially method two is this. You're going to multiply the numerator and denominator by the least common denominators of all of the fractions in the problem. And then you simplify what's left over. So with that, we're going to go through both of these methods. Example 4 takes us through method 1, where you basically work out any math problem that appears in the numerator or denominator, and then you divide by multiplying by the reciprocal of the divisor. So, for instance, you're going to see that we're going to go ahead and simplify this denominator first by adding those two fractions together. So here we have x plus 1 over 15 plus 4 over 15. Since these denominators are the same, we can actually just add those numerators together. You get x plus 5 over 15. And now we have division of two fractions. So throwing back to section 8.4, you might recall that we actually multiply by the reciprocal of the divisor. So you'll see that they swapped out the division for a multiplication symbol. And then the reciprocal of our divisor is going to be 15 over x plus 5. And I'm going to cross reduce my 5 and my 15. 5 goes into 5 one time, and 5 goes into 15 3 times. So now I can just, you know, treat the 5x like it's 1x and the 15 like it's 3. And then I do 8 times 3, multiply straight across to get 24. And then I have x times the quantity of x plus 5 on the bottom. And you could leave it like that. You know, we're trying to get in the habit of leaving our answers in factored and reduced form. So that's actually done. That's the end. So method 1 is just like that. Now, method 2 comes in handy when you have a lot of different denominators going on in the problem. But step 1 is to find the LCD of all of the fractions in the numerator and denominator. So your eyes have to go to every fraction in the problem there. So essentially I'm tasked with finding the LCD between 3x and x plus 1. And if you bring down the thing that's on the left and compare it with what's on the right and insert your missing factors, your LCD is indeed 3x times x plus 1. And what we're going to go ahead and do is multiply the numerator and denominator by this LCD of 3x times x plus 1 and 3x times x plus 1. Essentially all I've done, since I'm multiplying it by the top and bottom, I'm basically just multiplying this original fraction by 1. So I'm not changing the numeric value of the top or the bottom because I'm essentially just multiplying the entire fraction by a factor of 1. Remember when I multiply, I kind of distribute this LCD to my fraction. So when I do this, you know, I do show a little bit of scratch work, and here's how I show it. I copy down the original fraction that's in my numerator. And when I multiply that numerator by 3x times the quantity of x plus 1, you know, that's kind of all over 1. So the top is actually all that gets changed. Essentially, I just plop that LCD right on the top of that fraction. And then I, very much do the same with the bottom, except there's a little bit of the distributive property that's going to play into this one. So I copy down my original denominator, and essentially what I'm doing is I'm multiplying that entire denominator by 3x times x plus 1 over 1, and if I multiply fractions straight across, I essentially just end up distributing that LCD to the top of each fraction. So it did go to both things. Now what's so awesome about this now, looks like a mess, but in actuality I can now cross off or cancel my denominator. So for instance, I can reduce this top fraction here by reducing out that factor of x plus 1. And then on the bottom, I can reduce out a 3x and then an x plus 1. So look at what I have left over. On the top, I just have 2x times 3x. And now on the bottom, I have x plus 1 plus 2 times 3x. This isn't too bad. I can go ahead and simplify this now. 2x times 3x is 6x squared. And the bottom, essentially I have x plus 1 plus 6x. Or I could say that that's just 7x plus 1 on the bottom. And that does not reduce. It's done. So this method definitely has our advantages because we essentially just get rid of all of the denominators in the problem. That's the beauty of multiplying by the LCD. We use this particular scale quite a bit in section 8.6. So those are our two methods for simplifying a complex fraction. So now I'm going to give you just a few minutes to try a little bit of practice, and then I'll go ahead and post your answers for you. Okay, and I just wanted to show you your answers. So that's what they ended up looking like. You'll see that for number 1, I just real quick simplified the top, simplified the bottom, and then multiplied by the reciprocal of the divisor. And then on number 2, I tried method 2. I just grabbed the LCD of 2x squared, multiplied that on the top and bottom, and then just kind of got my denominators to all go away. It worked out pretty nicely. So I ended up with 5x plus 4 over 6 minus x. And those are all factored and simplified completely. So that I know I'm now done with the problem. So following this particular lesson, you'll see that you do have a little bit of bookwork. You would now be ready for 587, 31 to 36, just giving a couple problems a try. On Thursday, we're going to go ahead and do a little bit in-class practice with a worksheet, maybe some marker board work. And then on Friday, we're going to do a cumulative practice of adding and subtracting rational expressions and then simplifying complex fractions as well. All right, that concludes our notes for section 8.5.